I was worried about that. Okay. Um, yeah, one sec. Is this thing gonna work? Okay, great. Um, so yeah, as Ian mentioned, welcome to our seminar series talk for the US Computational Mechanics group at Berkeley. I'm Aaron, and I guess a little bit about me. I'm a second year PhD student, currently working under the supervision of Professor Papadopoulos. I work with the Computational Solid Mechanics Lab here at Berkeley. On my free time, I like to do photography, primarily street photography and street journalism. Some of my pictures are on the right here. I also like to skate, and honestly, I do everything art related. So yeah, just a little bit about me. So a brief overview of what I'll be going over for this particular talk. I wasn't expecting people to actually show up, so I suppose I should actually talk about a little bit about my personal background with respect to my academic journey here at Berkeley, which includes my motivations, some of my actual field interests or what helped shape that, how I came to actually choose my professor that I'm currently working with. And I'll transition into my actual research interests and what I'm looking into as of right now, which is very much a tentative work in progress, but we'll talk about it more along the way. Okay, so I started here, man, 7 years ago, I think. I originally began as a civil engineer, and my intention was to go into, I had a focus on structural mechanics, and my intention was to go into more so on the side of structural engineering and earthquake engineering, and do possibly research related to that. But unfortunately, as I got along the civil engineering curriculum, I found that there was a misalignment with my own interests and what the civil engineering curriculum at Berkeley provided. And I wasn't really satisfied or found very much academic fulfillment in my courses. So I decided to take a bit of a pivot, and I started taking some more mechanical engineering and mathematical methods courses. And eventually it wasn't until my senior year here that I found out what I really wanted to do. And it turned out to be within the realm of continuum mechanics. And from there on, once I knew that I actually wanted to go into continuum mechanics, the next question thereafter was like, okay, what can I actually do with this then? So I'll talk a little bit more about my actual motivations and underlying intentions with respect to what I wanted to do with continuum theory and how I got into that. So some preliminary discussions before I guess I get into more of the concrete details on my own academic journey. When I first started here, I think I wasn't entirely certain what I wanted to do. I kind of went off of civil engineering off of a whim because my brother was also a civil engineer, and I'd done an earthquake engineering project during my senior year when I was in high school. And I was just like, okay, let's just roll with that. That seems kind of cool. And when I first started, all I really knew is that I enjoyed math and physics. And I think that's about where everyone's starting point is when they first get into first start their undergraduate career. So, I liked a lot of things. I think at the time I was really into quantum mechanics, but that soon shifted, I think, during my junior year when I started taking more math and theoretical courses within my engineering curriculum. And I think it was particularly when I took the beginning engineering dynamics course, I think ME 104 with Professor Casey, that sort of pivoted, because I noticed that I had a pretty big affinity when it came to not just pure math related concepts, but actual applications within engineering theory and engineering physics. And I think this is where I started to transition less so from, or more so from, not having as much of an idea of what I wanted to do to focusing more so on structural mechanics and earthquake engineering. Consequently, I took some actual structural mechanics courses. I thought they were really cool, it's just, I think the way that we design our coursework and core curriculum here for undergraduates at Berkeley, at least within the civil department, I think is a little more oriented towards industry and actual application of the classes that you take so that you're prepared for getting an actual job, as opposed to doing more research or academia related uh, sort of interests. And so I thought it was really nice, but I still didn't really, there was like something missing within that particular niche in my interests. And I felt that there was like just a tiny gap in what I wanted to do. And that's when I took continuum mechanics with Professor Casey during my senior year at Berkeley. And I fell in love almost immediately with what the theory had to offer, and the foundations of this very general mathematical framework that we can use to analyze and study mechanics and dynamics concepts in a very broadband and general framework. So what actually is continuum mechanics then? Well, for the sake of brevity and not to lecture my own continuum students that are here today, the general essence of what this theory is oriented on is it's a way for us to describe the general motions, kinematics, and balance laws related to deformable bodies, subject to particular constraints and loadings. Generally, these translates to the classic angular and linear balance of momentum. The equations that you see on the right, the first set of equations you see on the right are the usual prescriptions for the boundary conditions and the strong form equations for a general continuum. Sans any other external conditions like thermal dissipation and other extraneous loading conditions that you can have. And then on the bottom is the associated weak form solutions that we can use to actually compute the displacements and stress fields and other things of interest with respect to continuum theory. So that's like a general overview of what continuum theory is. And it was during this time that I found that theory was really interesting, but it kind of felt like, okay, I've arrived at these governing differential equations to particularly describe a system that I'm interested in. But now what? I can't actually do anything with these equations that I formulated. So for me, it was that's when I started to develop an actual interest within the realm of computational mechanics, and actually putting these models that we've come up with and constitutive laws to work, and actually deriving or getting some tangible results out of them so that we can pressure test and validate the models that we come up with and see if they actually match reality in some respect or another. So that leads into my actual research interests and how they came to be. It's not? Okay, what should I, should I? Yeah, okay, let's try that. One sec. Is that okay? I have no idea. I guess you can let me know since you can see the screen.
Your screen is stuck right now.
Is it really? Oh. Where is it stuck on?
Stuck on the seminar opening.
Oh, that's not good. Okay, maybe
Maybe try resharing. Aaron.
yeah. Well, I
Yeah.
already did that. So should I just like unplug the HDMI cable?
I think you might have to share the slideshow.
Share the slideshow?
Yes, play the slideshow, then somehow go and share.
Okay. Yeah. Well, when I get to the actual slideshow, Okay, well, hold on one sec. Maybe I could just not. Okay, wait, so is it? Is it still stuck?
Slide up there, yeah.
Okay, can you let me know if it's stuck now? If I
It's stuck when you share.
Oh, when I actually share. Okay, so then what I'll do is I'll just I won't play from the slideshow, but I'll just
Or you can just go on which slide you're on right now.
yeah.
Keep the slide
Yeah,
left over.
no, I know. So just transition this way. Like this?
Yeah.
Okay.
You're-
Yeah.
I'll give you.
All right.
show you this.
Great. Sorry about that, everyone. Hopefully, all right, so just to briefly overview some of the slides that I went over. I am here. Yeah.
Oh,
Okay.
that.
Great. Yeah. Cool. So I think it was around this time that I started looking into what can I actually do with continuum mechanics. And that's when I actually reached out to some professors. And I think it was Professor Gu that I started shadowing in her research lab for a while, because I noticed that she had a broadband array of different research topics and interests within the field of solid mechanics and fluid mechanics, which I seem to be gravitated towards because I couldn't decide between one or the other. And eventually I did some research under her wing, and I worked on a project related to aeroelastic flutter with respect to aerodynamic loadings acting on airplane wing structures and airfoil wing structures, and understanding what propagates and what exacerbates the effects of the flutter phenomenon within, I guess, the realm of aeronautics. And I think it was within that transitional period where I had finished my undergraduate career and was waiting for my graduate school application results, that I found that there was a definite connection with respect to what I wanted to do at the intersection of theory and computational analysis to actually validate and pressure test the models that I was working with, and formulating an actual robust continuum theory for the governing equations of what I was interested in working in, and then validating those through some computational methodology or algorithm, particularly the finite element method. And these days, I'm particularly interested within the realm of continuum plasticity and continuum thermomechanics, which are incredibly involved theories within the realm of solid mechanics. And some of the precursory classes and knowledge that I'd acquired up until this point was getting a very strong or general solid foundation on continuum theory, understanding the pure and applied mathematical methods that we need to understand with respect to what shows up in these courses, particularly it's always analysis. So real analysis, complex analysis, functional analysis. Numerical methods are definitely pivotal and incredibly important, especially when it comes to actually doing computational research. And of course, if you're doing, depending on what you're actually doing, there's a whole world of different branches that you can go into with respect to the miscellaneous physics. So you can also have thermodynamic loadings and electromechanical loadings with respect to the problems that you're interested in. Anyway, so I think there was like this little gap semester that I was in where I was auditing Professor Casey and Professor Stagman's courses on foundations of continuum mechanics and nonlinear elasticity. And I think that helped broaden my background and give me a stronger sense of what I wanted to do. And it was after that class that I came up with this particular idea that I pitched to my professor about a year ago, which was, a lot of the problems that we work in with in the framework of solid mechanics are usually with respect to isothermal conditions. We don't really talk about the heat evolution or the thermodynamic evolution of the problems that we're concerned with. And it makes sense. More often than not, the actual mechanics and conditions that we're concerned with don't involve a lot of thermodynamic or heat conditions that come into play. But I'm often interested with respect to an actual generalized understanding of continuum theory and what we can actually do to broaden the range of which our models are applicable for more, I guess, extenuating circumstances that we can have on the loading criteria and the conditions that we apply to our problem of interest. And so it was then that my professor had mentioned this idea that what I was talking about seemed very similar to what goes on with respect to additive manufacturing and metal printing processes. Because, well, here, I guess I'll play this video to give you an example of what I mean. So this is a type of directed energy deposition additive manufacturing process where this powdered, I guess there's like an array of different type of situations that or methodologies that we have for metal printing. But in this particular case, we have metal filament being deposited within this nozzle, and then that metal filament is being heated up and then placed down on a substrate layer by layer, where it will conform to whatever the software requires it to, whatever geometry the software requires it to conform to. And then we end up with these engineering parts that are a lot faster to make, and they're a lot more cost effective. So it's a really attractive method to actually come up with these or develop these engineering parts that I guess are a lot more reliable to make and manufacture as opposed to our usual subtractive manufacturing methods with milling and other things related to that sort. And that leads us to the problem statement with respect to my related research. There have been previous research and different schools of thought with respect to conducting research with respect to simulating solidification processes in additive manufacturing, especially when it comes to directed energy deposition. And a lot of these models typically involve very linearized assumptions that, for better or worse, don't really accurately capture the actual thermal physics involved with the processes that are going on in here. What we have as a result of this quick thermodynamic solidification process with respect to metal printing is this inherently thermoviscoelastic process where the printing process is dependent or rate dependent. And so the actual material is dependent on the time or the thermal and thermomechanical history as it's being layered down on the substrate. And so there are a lot of moving parts that go into this. There's a growth process, or there's a surface growth process where this material is constantly having its surface added onto it through the addition of these new substrate layers. There's residual stresses coming in as a result of the thermomechanical processes embedded within this, what is effectively a thermal anisotropic process. We have a nonlinear viscoelastic response from the material as it's being created throughout this printing process. And let's see if there's anything else that is horrifically complicating this problem anymore. I think I think it's those main three things. So my professor has actually done some actual related research on modeling additive manufacturing methods. With this respective paper, it was in the context of modeling fused deposition processes in additive manufacturing, so things like thermoplastics and the likes. Effectively, what this came down to in his model was a simplified version of this thermoviscoelastic process into modeling what is effectively a transient heat transfer problem, directed onto a solid mechanics problem, where effectively what you have is this like Lagrangian configuration that's dependent on time. So you have this evolving reference configuration that's organically incorporating this growth process that's going on with respect to this additive manufacturing process. And so one of the nicer assumptions that we can make when it comes to modeling additive manufacturing is we can assume that the deformations are within the linear or the infinitesimal scale, because what is it called? I think it's I'm blanking out on the actual name, but there's this constant that I think is to the order of 10 to the -6. Oh, right. No, I just lost it. But anyway, so you have these large temperature dependencies strain away from thermal equilibrium. And regardless of how hot you make you are melting the metal filament, because it's being multiplied by this factor of something on the order of 10 to the -6, even if you're multiplying by a factor of a temperature on the scale of thousands of degrees, it still won't, the constitutive laws that come as a result of how we determined the deformations will still be on the order of, I think, millimeters. It's very small. So we can employ thermoelastic conditions in this case. And as I said before, he utilized this updated Lagrangian formulation imposed on this model where it's dependent on time, and we can solve for the residual stresses and carry them as inputs with respect to the updated reference configuration for for the governing equations that we're solving. And I think that's a really good starting point. But now the problem is there's something else quite implicit happening that needs to be properly captured in order to understand the qualitative behavior of what's really going on within these solidification processes. And if you think about it, as the melted metal is being deposited on the substrate, and the previous material that was created and is lagging behind and solidified is essentially going through a rapid phase transformation or phase transition, where it's turning from a liquid metal to a solid. And a lot of methods to actually simulate additive manufacturing, whether it be for metals or plastics, don't incorporate this phase transition, or if they do, they don't incorporate it very well. And that's a particular problem that we need to take into account for, because when you have these phase transitions, you effectively have this propagating surface of discontinuity where some arbitrary body is transitioning from a liquid or a solid state to a solid or liquid state, or I guess fluid, if you want to be pedantic about it. But that's essentially the premise of what we're working with. We have these inherent surfaces of discontinuity that are being introduced and are creating these inherent thermal anisotropies that are affecting the quality of the print that we end up with when we have the final print created. So these surfaces of discontinuities are a particular issue because they're there's convection at play that is creating these changes with respect to the mass density of the body of interest. And there have been some ways to alleviate the issues presented with respect to standard finite element modeling for solidification processes. Historically, what people have done to try to alleviate the Stefan problem is to utilize enthalpy evolution solvers and moving meshes methods. It's a weird way to phrase now that I say it out loud, but yeah, and it was like an honest attempt on itself, but it introduced, I think, more complications than it did actually try to resolve the actual issue at hand at properly formulating and accurately depicting the thermal physics at hand with respect to these processes. And so what people had tried to do thereafter is introduce this sort of enriched finite element method, also called the XFEM. I think it's called XFEM for extended finite element method. And what they do is akin to introducing a phase field, where they introduce functions with discontinuities and derivatives with discontinuities. And they allow the factor of this phase field defined on the bottom right, as you see right there, to serve as enrichment functions to the typical computational modeling when it comes to standard weak formulation in the finite element method. And this was also okay. The problem is that models of the models trying to depictate and solve the Stefan problem in this format typically falls under two categories. One is either the model was accurate but inefficient, and it's too computational costly to actually carry out, or they are efficient but inaccurate and don't actually properly capture the qualitative behavior of what's going on with respect to this phase transition process in additive manufacturing. And the other thing is they often decouple the thermal processes and the mechanical processes as two separate entities. And there's an inherent problem with that, because right from the get-go, when we're talking about these additive manufacturing methods, they are generally and inherently fully coupled equations. You can't really separate one from the other, or else you just get inaccuracies that don't really lead to certified results in your model. And so quite recently, actually, I think within the last year, there was a paper released in 2023, which I'm actually utilizing with respect to my research proposal on formulations of the actual kinematics involved with the additive manufacturing process, is a thermoviscoelastic model of the Stefan problem, which properly captures the rheological and mechanical phenomenon that is associated with this phase transition that can occur either within solidification processes of a fluid solidifying down to a solid, or a solid remelting into some sort of fluid. And this paper formulated the Stefan problem under a fully Eulerian model. And there's some potential issues with that. But in essence, I think this is a great starting point with respect to categorizing my research and actually creating a proper model that captures the viscoelastic response and behavior that goes on within metal printing. And we can utilize this and potentially conform it and adopt it to our liking, and in adopting a dynamic Lagrangian model as opposed to an Eulerian model. So in essence, what we have is this particular growth process where along the updated mesh for the configuration of the printed metal is we're going to be solving for this the Stefan problem using the associated constitutive laws and taking in the thermal history from that as input parameters for the updated Lagrangian configuration to properly capture all the moving pieces that are going on with respect to additive manufacturing and metal printing. So we can capture the growth process, so we can capture the residual stresses and how that will affect the shape errors with respect to the printed material, and understand the viscoelastic response of the material to varying degrees of accuracy, but primarily capture the proper qualitative behavior through this through the governing equations that arise from the phase transitions described in the Stefan problem. And yeah, I think that's about it with respect to my presentation.
So if you guys have any questions from the audience, and if you folks on Zoom, you just want to unmute yourself and, have any questions, then we got, plenty of time.
Yeah.
Why?
DED?
Right.
Yeah, what about it?
Why is that process? It's almost obsolete. Like a lot of people are doing modern.
Yeah, it's one example. I was just using it more so as a way to introduce the concept of additive manufacturing within metal printing. But a lot of the processes that are going on and being created for novel methods to print metal still follows along a similar idea of melting some metal filament and laying it down. Effectively, I was just trying to introduce the idea of these rapid solidification process that goes on kind of ubiquitously within metal printing, regardless of whatever additive manufacturing method you're utilizing.
The filament sometimes is different because once you deal with the powder bed fusion, you deal with a lot of powder.
Yeah.
So shooting laser out of powder is vastly different than just trying to have a filament of some sort and welding.
Yeah, but the process is still inherently a rapid solidification process when we're talking about additive manufacturing. There's still this like rapid cooling that's going on, where you have these large temperature deviations from thermodynamic equilibrium, and this whatever we're, I guess, I don't know if you're using laser sintering or directed energy deposition or powder bed fusions or what have you, whatever other metal printed methodologies are being created to this day, the process is still following along this format of this material that's being rapidly cooled down and conformed into whatever particular geometry or topology you're interested in. So it's that's just I think I use directed energy deposition more so as a pedagogical example to introduce the actual problem statement of what we're interested in. Effectively, this is trying to understand the Stefan problem in relation to additive manufacturing.
So essentially just look at the Stefan problem and use DED process as the one example.
Yeah. Yeah.
Besides, like, I know you mentioned moving meshes, but like in general, what are the main approaches to like actually simulating problems like additive manufacturing where you don't have like a set reference configuration?
Yeah. There's a couple of discrepancies and I guess inconsistencies with respect to how people are actually simulating additive manufacturing methods. Some people use a mixed configuration where they have the Lagrangian or Eulerian configuration or model, and some people are using a fully Eulerian model to properly emulate the fluid domain here actually. And this is like standard Stefan problem nomenclature right here in this particular diagram, where effectively it's like you have some general material body, and then within that material body is this surface of discontinuity where it can either be allocated as a fluid or a solid. And they separate or they distinguish this material into some particular separate boundaries where there's a distinct fluid and solid region. And there's a lot of difficulties because one argument is that there's a lot of difficulties in properly representing the Stefan problem in this format, because one argument is that we have a fluid structure interface problem where I guess you have to utilize both an Eulerian model to properly formulate the fluid region of the material and a Lagrangian model to describe the solid domain of the material. And that kind of complicates things. So it's kind of, honestly, it's kind of a toss-up with respect to the research done. And there's been a lot of inconsistencies and I don't think there's like been a proper general consensus and how people have treated this particular model and attempting to reconcile with all of the issues that come across this phase transition problem. I mean, one example is just to adopt a fully Eulerian approach, as my professor has done. But even that just effectively turns from a transient heat problem to a solid mechanics problem that doesn't capture the phase transition of what's going on. So it depends, really. There's a lot of, actually, I think that's one of the main issues is there isn't a lot of literature out there. And with respect to using the Stefan problem to model additive manufacturing, and the ones that are out there are very scarce and far few in between.
Alright, another follow-up question. Have you ever seen literature people attempting to model AMs through voxel-based methods?
No, I don't think so. I'm not too familiar with voxel-based methods myself, so.
Me neither.
Like planet fitness method. Or planet option.
Well, I mean, presumably not voxels, like, like 3D cubes that like represent the different kind of element, you could say.
Oh, voxel.
Yeah, so you did the heat shielding stuff off that on voxel?
Yeah, our advisor has done
Does-
3D printing stuff with boxes.
Ton of research.
Oh,
So they're in Missile by the professor.
Just go after this talk, just hit msol.berkeley.edu. Go to the publications and you'll find you link up.
oh, cool.
Yeah.
Yeah, so there is some, I know some where their lab does a voxel, but I'll let them talk about it instead of I pick it.
Yeah.
All right,
Any other questions?
any other question? Okay,
Regarding simulation, are these pretty much all finite element methods or are
Yeah.
element or material point methods also used?
Material point method. I feel like that'd be more. As far as I understand, I think material point methods are better suited for granular materials or anything that can be formulated as a granular mechanics problem. I suppose you might be able to do that to maybe understand the actual powder or filament that's being used for the metal, but to my knowledge, no, it is usually mostly finite element methods. That's pretty standard in the scope of computational mechanics in general, I think.
maybe I missed a big idea that I
Yeah.
missed. But when you're saying that current methods haven't fully captured the phase transition problem, like what parts, like, what are they missing?
Yeah, yeah. So with respect to this paper that I cited here, they're just the governing equations that they're using to dictate the problem here aren't incorporating any viscoelastic behavior from the material. They're using pure temperature and heat conduction governing equations to model the problem. And I think there's also some argument to be made that, I don't know, that the phase fields that they're using to represent the surfaces of discontinuity aren't very accurate in actually capturing the phenomenon that's going on with the phase transitions, because effectively, from what I understand anyway, in the related research, it's like they're just putting on an on-off switch with respect to whether or not the domain of the material is a fluid or a solid, but it doesn't really capture that proper transitional effect that goes on with respect to an actual phase transition. And I feel that if you're going to use it, I don't know, I have my own gripes with respect to phase fields, but I don't think it's very well suited for describing phase transitions as it is maybe fracture within damage mechanics or something. But yeah.
Transition.
Well, yeah, well, okay, there's some argument to be made there, I suppose. But that's what I mean when I'm saying it's still heavily polarizing topic that's being addressed in numerous ways. Maybe I think there's a better approach to be had with a rapid solidification process where you can effectively neglect the viscous effects with respect to its contribution that goes on in the solidification process. It may not be entirely accurate as opposed to having a fully nonlinear viscoelastic material model, but I think it's a way to circumvent the issue that comes across with that. But yeah, I don't know. It's fine. It's not bad. It's still there's still been moderate success found within papers that have utilized these formulations, but I don't know. I think everyone has their own approaches, and I think that's definitely a valid approach. But I think there's still work that could be done in better capturing the physics that goes on with the Stefan problem. No, not.
I'm muting Zoom to see people on Zoom.
Oh, okay.
I wasn't sure when I muted myself too, but.
Okay. Well, is anyone from the virtual audience have any questions? that they would like? You
I've
can
got
feel free to ask.
And
And
I'll put the speaker up on my side.
Aaron, can you hear me?
Okay, well, I don't know.
So one thing.
Okay. So.
Aaron, can you hear me?
Oh, Tim asked if you can.
You have them type it.
Yeah, maybe you can just type the question. That'd be easier.
Some papers that are read, most of the people that model DED
Mhm.
are assuming energy, the absorption energy of the, whether it's filament
Yeah.
or it's powder, is always, there's no losses. Like, I'm interested
Yeah.
to see what are you gonna say?
I think there is dissipation factors to incorporate on that end. I mean, you bring some sort of cooling process or some sort of fan to your metal printing process, and that generally will reduce the amount of shape errors that will come about with in the final printed product. And I mean, there's like some thermal convection phenomenon that's happening with respect to the heat that's being dissipated in this particular process. And I'm not sure it can be entirely neglected. I think to like
Sorry.
a moderate approx. Oh yeah.
Energy.
Yeah. Oh, the energy enhancements.
On buildings.
Yeah. That might be okay. But the energy output, I wouldn't be too sure on. But I also have to plead ignorance on that end because I haven't really looked into the energy input parameters so much as I have the whole overall physics. Okay, Tim, what did he say? Do chemomechanical effects ever play a role? I imagine impurities would have a significant effect on any anisotropy. Yeah, I'm sure there's a lot of processes that you can always tack on to this particular model and this particular situation. I'm not sure. I would also have to plead ignorance on that end. As like a default answer, I'd say probably, yeah, as much as other fully coupled mechanical processes are involved in this particular situation. But I think the main thing that we're interested in is understanding the qualitative behavior that comes as a result of the Stefan problem. That's my primary proposal and pitch for this particular research topic. But yeah, I'm sure how do you say that? Chemomechanical effects, yeah, play a role into this. Yeah. Well, is there any other questions? If not, I think we can just about wrap it up.
Yeah, okay, yeah, we can wrap it up. So thank you so much, everyone, for coming today. And this is the last little plug for this, that we are setting up a new student organization, the United States Association for Computational Mechanics, a student chapter, to set up a student chapter here at Berkeley. We have 3 more talks that are scheduled for the semester, and which one will be next week. It will be done by Teresa Honan. She was a former PhD student under Professor O'Reilly, who's now a professor at the American University in Beirut, and her research is on holonomics and how past. So you were here last semester about the BB8 talk about how the sphere rolling and those spherical robots. That's part of what her research, and that I think is a very fun talk for her to do, to talk about how you can model cylinder rolling and how the pass and how you turn. I think it's a very interesting and cool talk. So again, we have another one next week, Tuesday, same time. I'll bring coffee and donuts for in-person folks. So want to drop by at halftime? Thank you so much. Yeah.
Great.
Thanks so much.
Thanks for
coming.
showing up,
Appreciate it.
everyone.
Thank you everyone too for coming too.
Good job, Aaron.